Okay, let's unpack this. You ever feel like you're just swimming in a sea of information online?
Oh, constantly.
Trying to figure out what's actually important? It can feel impossible sometimes.
It really can. The sheer volume, it's staggering.
Right. And that's what we try to do here on the deep dive. Sort of wade through it all, pull out the nuggets you really need to know.
It's a huge challenge, isn't it? How do we actually make sense of all that digital information being created, like every single second?
Exactly. And today, we're diving deep into the world of data science. It's a field that's all about tackling that specific challenge head on. We've looked at a whole bunch of articles, some research, and it's pretty clear. Data science is, well, fundamental to understanding pretty much everything happening today.
Yeah, thinking about the big picture, data science isn't just some trendy buzzword anymore, is it?
No, not at all.
It really represents a fundamental shift in how we approach understanding the world, solving problems across, a huge range of areas.
So our mission for this deep dive, it's pretty simple. We want to give you a clear and hopefully interesting understanding of what data science actually is.
Right.
Why it's become so vital, and where it seems to be heading. And we promise we'll try to skip the super dense tech talk, ready to jump in.
Let's do it. So where do we even begin to define something that's, so broad and frankly, always changing like data science?
Good question. Let's maybe start with a formal definition. The U.S. Census Bureau, they have one. They call it a field of study that uses scientific methods, processes, and systems to extract knowledge and insights from data.
Knowledge and insights, that's key.
Yeah, and notice it highlights getting useful information from all kinds of data, so not just the neat stuff in spreadsheets.
That emphasis on diverse data sets is really interesting, I think. It points to how we've moved way beyond just structured data, right?
Totally.
We're dealing with the much more complex reality of modern info, which is often, unstructured, messy, images, text, video.
Absolutely. And what really makes data science work, what gives it its power, is that it pulls together different fields.
Right.
It's not just one thing.
Right, it's a blend.
It's like a fusion cuisine of statistics, computer science, maths, and crucially, a really good understanding of whatever specific area you're applying it to. That specific domain knowledge.
Exactly. That combination is the secret sauce, really. It's what allows data science to tackle these really complex, multifaceted problems.
Yeah.
Zooming out a bit, this blend, this multidisciplinary nature, it's what makes it so adaptable, so useful for all sorts of challenges, whether it's, figuring out customer preferences or helping doctors diagnose diseases faster.
Okay, so it's this interesting mix, but how did it actually come about? Like, where did data science start? Let's maybe look quickly at the history.
Okay.
Its roots, they actually go way back to the beginnings of statistics and computer science. Those are the foundations.
Yeah, and it's interesting, the term data science itself isn't brand new. Someone named Peter Nahr used it way back in 1974.
Noah.
Yeah, basically as another name for computer science at the time. And then later, in 1997, Jeff Wu actually suggested we should just rename the whole field of statistics to data science.
See, so the idea's been bubbling under for a while, but the formal recognition, that really kicked off around 2001.
Right, with William S. Cleveland.
Yeah, he essentially said, hold on, this is actually its own distinct field. He saw that with the growing amount and especially the complexity of data, we needed a more specialized set of skills, something that went beyond just traditional statistics or, basic programming.
Looking at the bigger picture, Cleveland's argument was really a key moment. It acknowledged that getting meaningful knowledge from modern data required this specific synergy of skills that hadn't really been formally recognized together before.
And then came the real game changer.
Yeah.
Big data. Early 21st century.
Ah, yes. The big data explosion.
Suddenly, we weren't just dealing with more data, but these massive, incredibly complex collections of information that weren't organized neatly at all.
Oh.
Unstructured stuff.
Right. Text, social media feeds, sensor data.
Exactly. And the traditional methods, they just couldn't handle it. They weren't built for that scale or that messiness. That's when data science really jumped into the spotlight. It became the essential toolkit for making any sense of all this information. Imagine trying to understand, all the clicks and interactions on a giant website every single day.
Yeah, traditional databases and tools just weren't up to the task.
No way.
And this brings up, I think, an important point about the sheer scale of modern data. It's not just the volume, it's the velocity, how fast it's generated, and the variety, the different forms it takes.
Right.
That created a huge demand for entirely new ways to store it, process it, analyze it. And that's where data science became absolutely vital.
Exactly. And this whole shift led to data science being called the fourth paradigm of scientific discovery.
Ah, the four paradigm.
Yeah, you've got your classic experiments, your theoretical work, computational simulations, and now data-driven science. The data itself becomes a primary engine for discovery.
So instead of always starting with a hypothesis you want to test.
Right. You might just explore a massive data set, like all those website interactions, and the data itself can reveal unexpected patterns. It can drive new questions you wouldn't have even thought to ask otherwise.
It's a really interesting shift in how science gets done, isn't it? Data-driven discovery lets us find patterns, gain knowledge at this incredible scale. Sometimes without even starting with a specific theory we're trying to prove. It just opens up totally new avenues for understanding.
And just to underline how big a deal this field became, remember that Harvard Business Review article back in 2012?
Oh yeah, the sexiest job one.
The sexiest job of the 21st century. I mean, that really shows how much attention, how much importance the field gained almost overnight.
Thinking about it, that headline, while catchy, wasn't just hype, was it?
No.
It reflected a genuine understanding in the business world and beyond of how absolutely crucial data scientists were becoming for navigating this new, information-rich landscape we all live in now.
Okay, so we've got a handle on what it is. What aspects would you like us to explore further in a future session? Let us know.
We'd love to hear what areas you find most intriguing or want to understand better.
Now let's dig into the core ideas, the sort of foundational pillars that data science is built on.
Right, the building blocks.
And like we touched on, it's all about bringing different fields together. You've got computer science, programming, then statistics, and machine learning.
Yeah.
And that really critical piece, domain knowledge.
Yeah, that interdisciplinary foundation is absolutely the key. Each of those areas brings essential tools, essential ways of thinking. And when you put them all together, you get this really powerful methodology for tackling complex, data-driven problems.
Let's break them down. Start with statistics. I mean, at its heart, data science is about using numbers, right?
Fundamentally, yes.
Statistics gives us the methods, how to collect the data properly, how to analyze it, interpret it, present it, all so we can actually make informed decisions based on it.
Exactly. So once we've gathered all this raw data, statistics helps us make sense of it. That starts with the basics, like descriptive statistics, summaries, averages, percentages, just to get a feel for the data, understand its main features.
Right, like getting the lay of the land.
Precisely. But then you have inferential statistics, which is about using the data you have to make educated guesses or inferences about a larger group or about what might happen in the future.
Okay, so descriptive tells you what is in your data. Inferential helps you guess about what isn't directly in your data.
That's a good way to put it. Think of it like a detective gathering clues, that's the data, and then using statistical tests, the inferential part, to see if there's enough strong evidence to confidently say, okay, this pattern I'm seeing is real. It's not just random chance. Or based on this sample, the suspect is likely guilty.
Right, and that connects to hypothesis testing, doesn't it? Making sure the patterns we think we see are actually meaningful.
Absolutely. Hypothesis testing is crucial for validating findings, ensuring we're not just chasing noise in the data. Plus, stats helps us understand probability, uncertainty, and it's a huge part of business intelligence, helping companies spot important trends in their operations or markets.
Got it. So statistics provides that rigorous foundation.
Looking at the bigger picture, yes. It provides the essential framework for making sure that the insights we pull from data are statistically sound, reliable, trustworthy.
Okay, now let's talk machine learning, or ML. This is where things get really interesting for a lot of people.
This is where the learning part comes in.
We're talking about algorithms here, basically. Sets of computer instructions, but algorithms that can learn from data. They figure out patterns and make decisions without being explicitly programmed for every single scenario.
And the key is they improve over time. The more data they process, generally, the better they become at whatever task they're designed for.
That ability to learn, to adapt based on new data, that's what makes ML so powerful, right?
Hugely powerful. It allows us to automate the process of finding complex patterns, significantly improve our ability to predict future outcomes, and even things like cleaning and organizing messy data more effectively.
And there are different ways these algorithms learn, aren't there?
That's right. There are several main paradigms. You've got supervised learning.
Okay, what's that?
That's where you train the algorithm using data that's already been labeled with the correct answer. So, like your example earlier, you feed it thousands of pictures labeled cat and thousands labeled dog. And it learns the features that distinguish cats from dogs based on those labels.
Okay, so it has a supervisor telling it the right answers during training. Makes sense.
Exactly. Then you have unsupervised learning. Here, the data is unlabeled.
So no answers provided.
Nope. The algorithm has to find structure or patterns in the data all by itself. A common example is clustering, grouping similar data points together without knowing beforehand what the groups represent. Or think about spam filters in your email.
Ah, okay. How does that work?
Well, they often use unsupervised learning to identify emails that share common characteristics typically found in spam, even without a giant pre-labeled list of every possible spam message. It spots the patterns.
Gotcha. Okay, supervised, unsupervised, any others?
There's semi-supervised learning, which, as the name suggests, uses a mix of labeled and unlabeled data. Often you have a little bit of labeled data and a lot of unlabeled data, and it tries to leverage both.
Okay.
And then there's reinforcement learning. This one's a bit different. The system learns through trial and error, essentially. It takes actions in an environment, and it receives rewards or penalties based on those actions.
Like training a dog with treats.
Yeah.
Or maybe like how an AI learns to play a complex video game.
Precisely. It learns strategies over time that maximize its cumulative reward. Very powerful for things like robotics, game playing, optimization problems.
Wow. So supervised, unsupervised, semi-supervised, reinforcement. Quite a range.
It's interesting to consider how this variety of learning approaches means machine learning can be applied to many different kinds of data and solve a vast array of problems.
And ML is behind so much stuff we use every single day, often without even realizing it.
Oh, absolutely. Think about the recommendation systems on Netflix or Spotify suggesting movies or songs you might like.
Yeah, those are eerily good sometimes.
That's ML analyzing your past behavior and the behavior of similar users. Or think about fraud detection systems for your credit card.
Right, getting that text asking, did you just spend $500 on llama wool?
Implied chuckle. Exactly. That's often an ML model flagging a transaction that looks unusual compared to your normal spending patterns. Or even in healthcare, systems that help predict a patient's risk for developing certain diseases based on their health records.
So it's really embedded in a lot of applications.
Zooming out, machine learning is really a key driver of automation, prediction, and adding intelligence to data-driven applications across pretty much every industry you can think of.
Okay, powerful stuff. What aspects would you like us to explore further in a future session? Let us know.
We'd love to hear what areas you find most intriguing or want to understand better.
But you can't actually do any of this data science, the stats, or the ML without the right tools, right?
Correct. The tools of the trade are essential.
So let's talk programming languages and specific tools. Being able to write code seems absolutely critical.
It really is. Programming skills are essential for everything from cleaning and manipulating the raw data to building and training those machine learning models, creating visualizations to understand the results, and actually deploying these solutions so they can be used.
And are there specific languages that are dominant?
Yes, definitely. Python and R have really emerged as the two major players in the data science world.
Okay, Python and R. Why those two?
Well, Python has become incredibly popular. It's very versatile, relatively easy to learn, and it has this amazing ecosystem of libraries specifically built for data science.
Libraries, like pre-written code module.
Exactly. Things like NumPy for efficient numerical calculations, Pandas, which is fantastic for organizing and manipulating data. Think of it like a super-powered spreadsheet you control with code.
Ah, Pandas, I've heard of that one.
And scikit-learn, which provides a huge range of standard machine learning algorithms ready to use. Python's a real workhorse.
Okay. And
R has its roots very firmly in statistics. It was developed by statisticians for statisticians, so it's incredibly powerful for complex statistical analysis and especially for creating really high-quality, insightful data visualizations, charts, and graphs.
So Python more general purpose, R maybe more specialized for stats and viz.
That's a common view, though both can do a lot. Python's versatility and large community give it maybe a slight edge in general ML deployment, while R remains a favorite in academia and for specific statistical tasks. And we can't forget SQL.
SQL, structured query language for databases.
Precisely. Most data still lives in databases, so knowing SQL is fundamental for actually retrieving the data you need to analyze in the first place. You need to be able to ask the database for the right information.
Got it. So Python, R, SQL, essential languages. What about visualizing the data, making it understandable?
Crucial step. Data visualization tools are key. You have dedicated software like Tableau and Power BI, which allow you to create interactive dashboards and reports, often with a drag-and-drop interface.
Right, for business users maybe?
Often, yes. But data scientists use them too. And then within Python and R, you have powerful visualization libraries. Python has Matplotlib, Seaborn Plotly, R has ggplot2, and others.
And what do these do?
They let you take all those complex numbers and findings and turn them into visual representations, charts, graphs, heat maps, scatter plots. This is often the best way to reveal hidden patterns, trends, and outliers, and crucially, to communicate those findings effectively to others, people who might not be data experts.
Makes sense. A good chart can tell a story much better than a table of numbers.
Absolutely. Oh, and one more tool worth mentioning, especially when dealing with really massive data sets, we're talking terabytes or petabytes, is Apache Spark.
Spark? What's that for?
It's a framework for distributed computing. It allows you to process huge amounts of data much faster by spreading the work across many computers, like a cluster, all working together, essential for big data tasks.
Okay, so a whole toolkit of languages and software.
Looking at the bigger picture, yes. Proficiency with these tools is what enables data scientists to actually perform the analysis, build the models, and, very importantly, communicate their findings in a clear and compelling way.
Okay, we've hit the stats, the machine learning, the coding tools, but there's one more really important piece we mentioned earlier, domain knowledge.
Ah, yes, the context. This is so important.
Explain that. What is domain knowledge in this context?
It's basically having a specialized understanding of the specific field or industry where you're applying data science. So if you're working in healthcare, it's understanding medicine, biology, hospital workflows. If you're in finance, it's knowing about markets, regulations, financial instruments.
And why is that so critical? Can't you just be good at the math and the coding?
You could be the best coder, the best statistician in the world. But if you don't understand the context of the problem you're trying to solve, your work might be technically brilliant, but ultimately useless or even harmful.
How so?
Well, domain knowledge is crucial at every single stage. It helps you identify the right business problems to tackle in the first place. It helps you ask the right questions of the data. It guides you in selecting the relevant data features to focus on, choosing the most appropriate analytical techniques, and critically interpreting the results correctly.
So it stops you from building a model that works technically, but doesn't actually address the real-world needs.
Exactly. Or a model that produces results that seem statistically significant, but are actually meaningless or misleading in the real-world context because you didn't understand the underlying factors at play.
Give me an example, maybe.
Okay, imagine building a model to predict customer churn, customers leaving a service. A purely technical approach might find some correlations, maybe people who click a certain button churn more. But someone with domain knowledge of the product and customer behavior might know that why they click that button is the real issue. Maybe it's a sign of frustration with a confusing feature. The domain expert can guide the analysis towards more meaningful factors and help interpret the why behind the numbers.
Got it. So it provides the meaning behind the metrics.
Precisely. And this is where the data scientist often acts as a bridge or maybe a translator.
Translator.
Yeah, translating the complex business problems into technical questions that data science can answer, and then translating the complex technical results back into actionable insights that business leaders can understand and use. This requires really strong communication skills too.
So it's not just about being good with computers and math. You need to understand the business and be able to talk to people.
Absolutely. That blend of technical depth, domain expertise, and communication ability is really the ideal for a data scientist.
Zooming out then, the ability to connect the technical analysis with practical real-world understanding is what ensures data science actually delivers tangible, valuable outcomes, not just interesting R&D projects.
Couldn't agree more. That connection is vital.
All right, foundation laid. What aspects would you like us to explore further in a future session? Let us know.
We'd love to hear what areas you find most intriguing or want to understand better. Okay, so that brings us to machine learning. The engine, really.
Where computers learn without us telling them exactly what to do step by step.
Precisely. Arthur Samuel coined the term machine learning way back in '59. Self-teaching computers, he called them.
After an AI winter, it got more practical, more statistical in the 90s.
Yeah, focused on learning from data patterns. Early ideas were around like Turing's concepts, Samuel's checkers program that improved itself.
So supervised learning, that's the one we probably bump into most.
Probably. The key is labeled data. You give it inputs and the right outputs, it learns the mapping.
So it can predict outputs for new inputs later on.
Exactly. Two main types. Classification predicting categories like spam or not spam.
Finding the dividing line.
Right. And regression predicting continuous values, like a house price. Finding the best fit line.
And many of these algorithms came from statistics originally.
Oh, definitely. Linear regression. Roots in astronomy centuries ago. Logistic regression. Decision trees all started as statistical tools before becoming core ML algorithms. Even SVMs grew out of statistical learning theory.
Fascinating. And the uses are everywhere. Image recognition, fraud detection.
Spam filters, medical diagnosis, predicting churn, loads of applications.
Okay, then unsupervised learning. The flip side.
Yeah, this is about finding patterns in unlabeled data. No answers given. The machine finds structure based on similarity or difference.
Like finding groups.
Exactly. That's clustering grouping similar points. Think customer segmentation. K-means is a classic example.
And the other tag.
Dimensionality reduction. Simplifying data by reducing features but keeping the main info. PCA is a big one here.
Where do these ideas come from?
Clustering has roots in anthropology, psychology. K-means was computationally looked at in the 50s. PCA is also an older analysis technique.
So this is good for exploring data, finding anomalies, maybe prepping data for supervised learning.
Absolutely. Customer segmentation, anomaly detection, organizing documents, visualization, often a first step.
Right. Now, deep learning. This feels like the really cutting-edge stuff.
It's a subfield of ML using these multi-layered neural networks. The core idea, mimicking the brain, is actually quite old, 40s, 50s.
But it had its own winter, then came back.
It did. Backpropagation in the 80s was huge, a way to actually train these deep nets. Then specialized types like CNNs for images, RNNs for sequences.
And LSTM solved a big problem with RNNs.
Yes, the vanishing gradient problem. Nets would forget early information. LSTMs from the mid-90s have special gates to control information flow, letting them learn long-term patterns. That was a game changer.
So how does it train? Backpropagation.
Yeah, data goes forward, error calculated, then calculus, the chain rule, sends the error signal backward to adjust all the connections, the weights to minimize that error, using optimization like gradient descent.
And CNNs use filters for images, LSTMs use gates for sequences.
Exactly. Deep learning's behind breakthroughs in image recognition, NLP, autonomous systems facial recognition, chatbots, self-driving tech.
Okay, one more pillar. Reinforcement learning. This sounds different again.
It is. Here, an agent learns by interacting with an environment. Trial and error, basically. It gets rewards or penalties.
Learning from feedback.
Right. Origins are cool, a mix of psychology, like learning from consequences, and optimal control theory from engineering. Bellman's work on decision processes.
How does it work, like mechanically?
An agent is in a state, takes an action, the environment changes, gives a reward. The goal. Find a strategy, a policy to maximize total reward over time, even if it's delayed. Algorithms like Q-learning help figure out the value of actions and states.
Perfect for games, right? Like AlphaGo.
Absolutely. Game AI, robotics, autonomous driving decisions, optimizing complex systems, even some recommendation systems, anywhere with delayed rewards.
So, pulling it all together, these pillars, math stats, the ML types, they all build on each other.
Definitely. Math gives the tools, ML uses them to predict, discover, decide, and many algorithms evolve from older ideas.
And you see this unifying theme, optimization.
Yes, that's a key insight. Whether minimizing error, refining clusters, or maximizing rewards, it's all about efficiently optimizing some complex function.
Calculus provides the direction, linear algebra handles the computation, stats defines the goal.
And optimization algorithms do the work. That's what makes the theory practical.
So understanding this history, these mechanics, it shows how abstract ideas become real-world tools. It's not static, it keeps evolving.
Which leads to a final thought, right? As data gets bigger, problems get harder. What's next?
Yeah, what new math or computing ideas will we need to push data science even further? Something for you to think about. Now let's talk impact. The real world effects, because data science is, it's genuinely changing things, isn't it?
Oh, profoundly. It's having a truly transformative influence across almost every sector imaginable.
What's the core mechanism?
At its heart, it's about enabling organizations to make much more informed decisions. By analyzing the vast amounts of data they collect, historical data, real-time data, they can gain deeper insights into their operations, their customers, their markets.
And use those insights to do what?
To forecast future trends more accurately, to optimize their processes for better efficiency, to identify and mitigate potential risks, and ultimately to gain a significant competitive advantage.
And I guess when you layer artificial intelligence, AI, on top of data science, it just ramps everything up.
Exactly. AI, particularly machine learning, amplifies these capabilities dramatically. It allows for automation of complex analysis, enables much more sophisticated predictions, and drives efficiency and accuracy to levels that just weren't possible before.
It feels like we've moved beyond just looking back at data, too.
That's a key point. We've progressed along a spectrum of analytics. First came descriptive analytics, basically, using data to understand what happened in the past.
Okay, reporting historical facts.
Right. Then came predictive analytics, using past data to forecast what is likely to happen in the future.
Predicting trends, customer behavior.
Exactly. And now, increasingly, we're seeing prescriptive analytics. This goes a step further and actually recommends what action should be taken based on those predictions to achieve a desired outcome.
Wow. So not just what will happen, but what to do about it.
Precisely. That progression really highlights the growing impact and sophistication of data science applications.
Let's get concrete. Talk about some specific industries. Healthcare seems like a huge one.
Absolutely massive impact in healthcare. Think about electronic health records, EHRs, all that digital patient data.
Yeah, mountains of it.
Data science analyzes that, plus data from clinical trials, even data from wearable fitness trackers.
Like Fitbits and smartwatches.
Yeah, to achieve incredible things, helping doctors detect diseases earlier, sometimes even before symptoms are obvious, enabling personalized medicine, tailoring treatments to an individual's genetic makeup or specific condition.
That sounds revolutionary.
It really is.
Yeah.
Also optimizing hospital operations, things like predicting patient admission rates to manage staffing levels better, reducing wait times, even detecting healthcare fraud.
And during the pandemic.
Oh, data science was absolutely critical during COVID-19, tracking the spread, understanding risk factors, modeling the impact of interventions, optimizing vaccine distribution. It was central to the global response. And now we're seeing AI algorithms getting remarkably good at analyzing medical images like X-rays or MRIs to help radiologists spot signs of diseases like cancer much earlier.
Incredible. So it's not just efficiency, it's literally saving lives and improving patient outcomes.
Looking at the bigger picture in healthcare, yes. It's fundamentally changing how medical services are discovered, delivered, and managed.
Okay, what about finance? Banks, trading.
Another sector transformed by data science. They use it extensively for risk management, assessing credit risk for loans, modeling market fluctuations. Fraud detection is huge, like we mentioned with credit cards. Analyzing transaction patterns in real time to flag suspicious activity, helping with anti-money laundering efforts. And then there's algorithmic trading.
The high-speed computer trading.
Exactly. Sophisticated algorithms analyze vast amounts of market data, news feeds, social media sentiment, everything, to make split-second trading decisions, often much faster than any human could.
So it's driving efficiency and security there too.
This brings up an important point about maintaining stability and trust in financial systems. Data science provides the tools to manage complex risks and combat increasingly sophisticated financial crime, protecting both institutions and consumers.
Makes sense. Okay, moving on. Retail and e-commerce. I feel like we see data science very directly there as consumers.
Oh, absolutely. It's all about understanding customer behavior, optimizing inventory, streamlining the supply chain, and ultimately personalizing the shopping experience.
Those recommendations, Netflix, Amazon, they know me too well.
Implied agreement. That's classic data science. Analyzing your past viewing or purchase history, comparing it to millions of other users to predict what else you might like. Dynamic pricing is another one, where prices change based on demand or even individual user profiles.
Yeah, I've seen that with flights and hotels.
Inventory management, too, predicting demand for different products to avoid stockouts or overstocking. Analyzing customer reviews and feedback to improve products. Predicting customer lifetime value. It's pervasive in retail.
So really tailoring everything to the individual customer.
It's interesting, the level of personalization data science enables is quite extraordinary, creating these very bespoke experiences based on deep analysis of individual preferences and behavior patterns.
What about marketing? Seems closely related to retail.
Very closely related. Data science helps marketers optimize their campaigns, gain deeper customer insights, and generally make their spending much more efficient.
How?
by identifying very specific microsegments of potential customers, understanding how people interact with the brand across different channels, website, social media, email, figuring out which channels are most effective for which messages, analyzing social media sentiment.
Like whether people are talking positively or negatively about a product.
Exactly. Lead scoring, predicting which potential customers are most likely to actually buy something. Customer segmentation, market basket analysis, figuring out which products are often bought together.
What?
Predicting customer churn, like we talked about earlier. It helps make marketing much more targeted and data-driven.
So moving away from just blasting everyone with the same ad.
Zooming out, yes. Data science is pushing marketing from broad, often wasteful approaches towards much more precise, measurable, and effective ways of engaging with specific, relevant audiences.
Okay, not just customer-facing stuff though, right? What about like manufacturing, logistics, the behind-the-scenes stuff?
Big impact there, too. Predicting demand for manufactured goods, like we mentioned for retail inventory, but on the production side. Optimizing complex global supply chains, figuring out the best sourcing, production schedules, shipping routes.
Trying to avoid those supply chain bottlenecks we heard so much about.
Exactly. Data science helps model those complex systems, account for potential disruptions, and allocate resources more effectively. Optimizing delivery routes for logistics companies to save fuel and time. Forecasting demand for maintenance services, identifying potential bottlenecks in production lines before they cause major delays.
So driving efficiency and cost savings in the physical world too.
This is where we see data science yielding significant improvements in operational efficiency, reducing waste, ensuring smoother flows of goods and materials, which ultimately benefits the whole economy.
What aspects would you like us to explore further in a future session? Let us know.
We'd love to hear what areas you find most intriguing or want to understand better.
Okay, and with all this power, especially with AI and ML making decisions, trust becomes a big issue, right?
A massive issue. And that brings us to two other critical trends: explainable AI, XAI, and responsible AI.
Explainable AI, XAI, what's the goal there?
The goal is to make the decisions and predictions made by complex machine learning models, especially black box models like deep neural networks, understandable to humans. Why did the model approve this loan but deny that one? Why did it make this specific medical diagnosis suggestion?
Right, because if you don't know why, it's hard to trust it or fix it if it's wrong.
Precisely. XAI techniques aim to provide interpretable explanations for model outputs. This helps data scientists improve their models, helps organizations meet regulatory requirements, especially in areas like finance and healthcare, and crucially helps build trust with users and stakeholders. It allows you to trace errors, identify potential biases.
Which leads nicely into responsible AI. That sounds broader.
It is broader. Responsible AI is more of a governance framework or methodology for developing, deploying, and managing AI systems in a way that aligns with ethical principles and societal values. It encompasses fairness, accountability, transparency, privacy, security, reliability. Basically, ensuring AI systems behave ethically and benefit humanity.
So XAI is part of responsible AI.
You could see XAI as a key technical enabler for achieving aspects of responsible AI, particularly transparency and accountability. There's growing concern that AI adoption is outpacing the implementation of proper governance structures. Responsible AI aims to close that gap, making ethical considerations mandatory, not optional.
Are these just nice to haves, or are they becoming essential?
Increasingly essential. Regulatory pressure is growing globally. And beyond compliance, ensuring fairness and mitigating bias through XAI and responsible AI practices can actually be a catalyst for innovation, leading to better, more robust, and more widely accepted AI systems.
Okay.
Another area gaining traction is augmented analytics.
Augmented.
This uses AI and ML to automate many of the manual tasks involved in data preparation and analysis. The idea is to make it easier for people who aren't expert data scientists, like business analysts or managers, to explore data and extract insights themselves, often using natural language queries. It aims to democratize data analysis.
Interesting. Making data insights more accessible across an organization.
Exactly. So lots of interconnected trends pushing the field forward.
Okay, let's try to wrap this deep dive up. Feels like we've covered a lot of ground.
We certainly have. It's a rich topic.
So just to summarize the key takeaways. Data science, it's this incredibly powerful, dynamic field. It's not just one discipline, but this blend of stats, computer science, domain knowledge.
Right. That interdisciplinary nature is fundamental.
It's got a fascinating history, growing out of those roots to tackle the challenge of big data. And its impact is just transformative across healthcare, finance, retail, government, even social good initiatives.
Absolutely. And it's not standing still. It's constantly evolving, driven heavily by these rapid advancements in AI and machine learning, new technologies like cloud and edge computing.
And, really importantly, this growing awareness and focus on the operational side, MLOs, and the ethical considerations, XAI, responsible AI.
Those aspects are becoming increasingly central to the practice of data science.
So hopefully, for you listening, you now have a pretty solid foundational understanding of what data science is all about. You know the core concepts, you've seen examples of how it's being applied, you've got a sense of the key trends shaping its future, and importantly, some of the challenges and ethical dimensions involved.
Zooming out, I think having this basic literacy in data science is becoming more and more valuable for everyone, really. Regardless of your specific job or field, it's touching so many aspects of our modern world. Understanding the basics is key to navigating it.
Definitely. So here's maybe a final thought for you to chew on. We've talked about the incredible potential of data science to help us understand the world, solve really complex problems, from curing diseases to tackling climate change.
Immense potential.
But we've also touched on the critical need for responsible, ethical implementation, addressing bias, ensuring privacy, maintaining transparency. So the provocative thought is, how do we strike that balance? And maybe what role do you think individuals as citizens, consumers, employees play in ensuring that balance is maintained as these technologies become even more powerful?
That's a great question to ponder. Where does the responsibility lie, and how can we all contribute to ensuring data science develops in a way that truly benefits society? It brings up interesting points about regulation, education, corporate responsibility.
Yeah. And if this deep dive has sparked your curiosity, maybe a specific application or one of the future trends or the ethical side, what aspects would you like us to explore further in a future session? Let us know.
We'd love to hear what areas you find most intriguing or want to understand better.